This is session 11 for models in epidemiology and biostatistics. My name is Gordon Hilton Fick. Well, in the previous 10 sessions, we have restricted attention to outcomes with exactly two levels. And we've seen the wide range of issues that impact on the analysis of tables with a dichotomous outcome and with models using the so-called logit link or logistic regression, and the very wide range of different models we might see. Well, now we're going to step into arguably the next most complicated circumstance, and that is when an outcome has more than two levels. And there are a range of issues here too, and a number of options for the health researcher in doing analysis when the outcomes have more than two levels. So what I thought I would do is take an example, a circumstance that will give us some context then, and it will illustrate, I think you'll see, the very wide range of circumstances that are available for the analyst. Okay, so let's consider a study in cancer research, and we're interested in a form of chemotherapy, and there are two types: a sequential type of chemotherapy and an alternating form of chemotherapy. And then there are outcomes, and for our purposes here, we'll suppose that the outcomes have been grouped into four mutually exclusive and exhaustive possibilities. And we'll use codes 1, 2, 3, 4. And so you'll see here that 1 then is a code for progression of the cancer. 2 is the code for no change, 3 for partial remission, and 4 for complete remission. So you can see that the larger the code, the better the outcome. And we'll come back to that. But for now, let's suppose that we view those four levels, if you like, of the outcome as merely different, but not necessarily reflecting an actual ordinal nature to their presentation. But we'll be coming back to that as well. Further, we'll suppose that we have an additional explanatory variable, and that is gender, and we are wondering if gender might be a confounder or a modifier. And we would then ask, well, how do we see modification and how do we see confounding in a situation in which the outcome is no longer dichotomous? Now, you might also be thinking, well, this perhaps looks like a case control study. We might have the status, say, at the present time, coded 1, 2, 3, 4, and then we looked into the past as to the form of chemotherapy. And so you might argue that, well, it is in fact the exposure here, the type of chemotherapy that was used, that is the outcome. And frankly, you could argue that this is the way to present this particular project. But we're going to take what is typically the way in which analysts, healthcare researchers, might wish to view this, and that is that the outcome will be the level of disease, as I mentioned. So this brings up another issue in that there are two, now from the start, there are essentially two different ways in which we might wish to discuss the disease exposure relationship here, and indeed what's the outcome and what's the exposure. All right. Let's now explore situations in which that issue is not directly present, and that is if we're concerned with the analysis of tables. So our starting point will be, well, we've got 4 levels of degree of disease, and we've got 2 levels of chemotherapy, and then we have a potential confounder modifier. Okay, so what's that? Well, we can see directly then that what we've really got is 2 2-by-2 tables if in fact we were in a situation where we wish to view both of those characteristics as dichotomous, but they're not. So now we've got, well, 2 4-by-2 tables. There are 4 rows and 2 columns. This inevitably gives us a collection of conditional probabilities. We have indeed the probability for the outcome in the ith level, given the jth chemotherapy and the kth gender. Oh, it looks a little bit, it's getting more complicated, isn't it? We've got now, oh boy, lots of probabilities. Well, let's display them. There they are. And we can see that, we've got the 2 forms of chemotherapy, sequential and alternating. We've got the males and the females, and we've got the 4 levels of the levels of disease, the levels of cancer. So you can see there they are. It looks on the face of it that there's 16 probabilities. But you might then notice that in fact we have several constraints on those probabilities. That is another complication, you could say, that, for example, amongst the males receiving the sequential form of chemotherapy, these individuals have outcomes 1, 2, 3, or 4, and clearly the sum of those 4 probabilities is 1. And that applies to each of the 4 chemotherapy gender groups here. Okay. Let's now, yes, we can notice that, in fact, there is, in fact, a constraint, and that I'm listing for you here. Okay, so the point here is that we've got lots of probabilities that could be explored in this analysis of this set of 2 4-by-2 tables. All right, let's take a look at a data set for this circumstance. Okay, we might want to explore this then. We've got the males and the females here coded. We've got male, female, and the males coded 0, the females coded 1. We've got those receiving sequential therapy, that's coded 0. The alternating therapy is coded 1, and then we have the 4 levels here of what we are now going to, at least provisionally, view as outcome, okay? On the other hand, as we'll see in a minute, we're going to be constructing an analysis that really doesn't necessarily, per se, specify what's outcome and what's exposure. I know. We might also notice here, and you would be attentive for noticing, that there were far fewer women in this study than there were men. And you can also see that some of the cells in this 4-by-2 table for the women were comparatively small. An issue that brings up how we go about determining that the calculations are sound and that the interpretations of those calculations are correct. Okay. And so we've got our ability to estimate probabilities. Right. Estimating the probabilities of proportions. And you'll notice I am continuing to be careful here and using the letter P for the probabilities and then putting hats over the probabilities or the P's when we have estimates. And we can notice, of course, that the sum of the four estimates in any row will be 1. Okay. So inevitably then, you might think, well, how about a test of significance for the men and a test of significance for the women? Well, although it may not have been mentioned so far in this series of sessions on models, Fisher's exact test can be used in this instance, even though it's not a 2x2 table. The methodology for constructing Fisher's exact tests extends to general R by C tables. And you might, and I would argue here, and I hope you would agree, that because of the small cells, especially with the women in the study, that using an exact method for determining a test of significance seems prudent. But you might then also observe that Fisher's exact test, which is, just to be clear here, it is essentially a two-sided circumstance. And there's a fair bit of technical matters connected here, but let's leave that aside. Okay, we have a general null hypothesis here, and I'm going to show you that in a second. But for the moment, we might see, is there any evidence of an association between the cancer classification and the chemotherapy classification? And in both cases, we see apparently no evidence. Well, we might then think, okay, are we done? Is that it? Is there anything more we can say? Well, most people would then say, wait a minute, what is that null hypothesis? Sure enough, I've got an exact p-value there from using Fisher's method. Of what null hypothesis, though? What is it? Well, it's a little bit technical. Here it is. We've got 2 of them. We've got one for the males and one for the females. And what are we suggesting? The probabilities, as we vary across the levels of the cancer diagnosis, don't depend on the classification of chemotherapy assignment. Okay, so that's saying that the probabilities with regard to the use of sequential chemotherapy are the same as the probabilities when using when the patients were receiving the alternating form of chemotherapy. And we have then a similar null hypothesis for the females. Okay, so we have one null hypothesis for the women, for the men, and one null hypothesis for the women. And you might think, all right, that makes sense. We're looking for whether or not we can determine if there's evidence that any of these probabilities are not equal. Well, as I have mentioned earlier in these sessions, both of these null hypotheses would be considered omnibus. They're not specific. They're not addressing any specific null hypothesis. Rather, they're addressing, well, a number of them. Yeah. There are, in fact, 3 degrees of freedom in both cases. Unspecified. The nature of those 3 degrees of freedom for the men and for the women is not specified. And we can see, for example, having seen, apparently at least, no indication that gender is modifying things, but again, we haven't really quantified what that might mean. But if we were to collapse these 2 4x2 tables into into one 4x2 table, well, what do we get? We get an association again. That's now a different null hypothesis, right? That is ignoring gender. Okay. So that says that, well, something's going on, we think. A, is it okay to collapse? And, well, we might provisionally say, let's just assume that we can. And then we face the assessment of these numbers when we don't consider the gender. So you could see this as a form of stratified analysis. We've got the two 4x2 tables, and we've got the crude 4x2 table. And what are we seeing here? Let's look at these percentages here, or these estimates of the probabilities. What can we see here? Well, if we were to compare the proportion experiencing a progression of disease in sequential with the proportion experiencing progression of disease in alternating, we can see that alternating appears to be worse than progression, than sequential. In the other groups, it's not nearly as clear, right? Well, here these two proportions are not that different. And in these two groups, again, not much apparently here. So is this low p-value here basically built around this? Is that the real issue? Is it about progression, ignoring or collapsing perhaps the other three? Or is there something more sensible or again, hidden in this analysis? We could go back and have a look at the stratified tables and look to see if the comparison between sequential and alternating with progression of disease is also seen. I'll leave you to have a look at that. Okay. Nevertheless, so what have we done? We've performed two tests of significance, stratified on gender, and then a test of significance collapsing the two 4x2 tables. And we get an indication that there is perhaps some interesting, there's something interesting happening here, but it's not entirely clear. And it certainly is true that while I have begun with the discussion of the essentially the stratified analysis with the tables here, many investigators would say that this methodology is not the route to go anymore. Or back in the day it might have been, but are there other options? And indeed, there are other options that were available to investigators some time ago, and that's what we're going to look at next. Okay. How about we suppose that we had planned in advance of looking at this data to compare the outcomes grouped. In other words, we'll compare those with improvement, that is groups 3 and 4, that is partial remission and complete remission, and compare the two groups, outcomes 1 and 2, where there was no improvement. And we could say, well, no improvement here, we would say, wow, that means either the disease has progressed or there's no change. And you might argue, well, is that collapsing a sensible thing to do? But in any case, suppose that was the game plan from the outset. All right, well, then we're back to two 2x2 tables and whether or not gender is modified or is a modifier or a confounder, right? But then we could ask, wait a minute, should I have been collapsing those categories? So one could argue here that before getting to what we might view as the primary null hypothesis in this project, if that's the way it was set out in advance, we have two secondary hypotheses that would be explored first. And that is whether the relationship between chemotherapy and outcomes 1 and 2 is present, given that there's no improvement, and similarly, a comparison between chemotherapy and outcomes 3 and 4, given that there was improvement. In other words, that really we've got 3 null hypotheses now. 2 of them we might review as provisional, or providing us with an indication that it is okay to collapse. And then, if possible, if perhaps we're comfortable with the results we see from A and B, that we would collapse and then explore that. Okay? So is the combining okay? Now you could argue then, if in fact, if we were to consider the assessment with A or B, that is the 2 so-called secondary null hypotheses, then we could argue that the plan collapsing would be misleading. If we saw some meaningful difference in either A or B, that the collapsing would be judged to be misleading or inappropriate. On the other hand, if we see no relationship in either A or B, then it suggests that we're in a sound place for addressing what was our primary null hypothesis, which was the assessment with the collapsed groups. Okay? So we end up with what is sometimes called a classic strategy. Right? We would very much like to compare, to look at the number 3 there, but we will first of all look at 1 and 2 and look to see if in fact the collapsing that's implied to address hypothesis 3 is at all credible. Okay, so this number 3 assessment would be considered after reviewing the results from the first 2 assessments. A pretty standard circumstance here. What are we doing? We have a primary null hypothesis that involves assumptions. And we begin our analysis by assessing those assumptions in the form of secondary null hypotheses. The primary null hypothesis being that it is option 3 is listed here. Okay. So, if we were to do this with Stata, it involves constructing some new variables, fairly easy to do. So there's the code for constructing the 3 new outcomes. We have the coding for progression, assuming that there is no improvement. We have the coding for partial remission, given that there is improvement. And then the third variable there, involving what would be the outcome for our, perhaps what we would judge to be the primary null hypothesis. Now, in each case, you can see here, I have presented the recoding in terms of the negative of the 2 outcomes. In other words, progression coded 1 and no change coded 0. Similarly here, partial remission coded 1 and complete remission coded 0. And finally, for our third, we code no improvement with 1 and improvement coded 0. Okay. The argument being here that then we're going to get 2x2 tables that have the negative characteristic on the numerator of the ratio. Okay. And sure enough, if we look at these 2 circumstances, if we look at, for example, the analysis first of the odds ratio for progression, right? And we do so for this is progression, assuming no improvement, right? So this is where we have selected a portion of the participants, those that had no improvement, and we're looking at, if I may, the odds of progression for those receiving alternating therapy relative to the odds of progression for those receiving the sequential form of therapy. And so what do we see here? We get an indication that we saw earlier with the individual data that, well, it would appear that although these two odds ratios are different, especially because of the women having only a small number in the study here, the confidence interval for this odds ratio for the women is quite wide. And the test of significance associated with gender modification is not significant. Nevertheless, from this analysis, we do appear to see that progression is associated with the type of chemotherapy, given we are restricting our attention to those who have no improvement. Okay? And in fact, we do see the Mantel-Hansel test here of the assumed common, because there being no evidence of modification, we might then address the assumed common odds ratio for progression. And what do we get? Well, we get some evidence, right? An association in this instance. On the other hand, if we repeat that analysis for those who did improve, in other words, we've done sometimes authors will call this a subgroup analysis, right? We've isolated out the individuals who had improvement and asked, is there evidence of more in the only partial remission group relative to the complete remission, ignoring the other two groups, right? And in this instance, I'll let you do the analyses again. No evidence that gender appears to modify here, and in this instance, no evidence of a difference between the two therapies. In other words, whether we were to use the crude or combined here, we would be saying that the odds of partial remission for those receiving alternating therapy relative to the odds of partial remission for those receiving sequential therapy could possibly be 1, right? That odds ratio could be 1. And in fact, we can see that the confidence limits include the null, and the test, for example, the Mantel-Hansel test, is not significant. Okay, so here's an example of a circumstance in which one of the two analyses, provisional, maybe you would judge here, secondary analyses, shows an association and the other one does not. Should I proceed with a collapsing in this instance? The planned analysis was to collapse the two progression groups, or progression and no change, and collapse the partial and complete. But this result is a little bit blurry, right? Well, we see that the justification for collapsing is you could say is suspect here. Should I be doing this collapsing? Okay. Nevertheless, if we were to proceed with the collapsed analysis, then what do we see? This is whether we should be or not, right? But if we are now looking at the odds of no improvement for those receiving alternating relative to the odds of improvement for those receiving sequential, we get, for both the men and the women, an indication that there is a relationship between the odds of no improvement in those two groups, right? The odds ratio is not 1. On the other hand, you would say, getting pretty borderline here, isn't it? Because, well, this confidence interval for the males, pretty wide, even wider for the women. And what are we seeing here? Oh boy, very borderline. The lower limit here for the crude and the lower limit for the combined are very close to 1. All right. The test of significance using the Mantel-Hansel method is correctly telling us that, well, that lower limit there is greater than 1. Yeah. So you see, we've got another dilemma, don't we? We've got, is this analysis? We've got first of all the issue of whether we should have collapsed, because we saw something when we compared the odds of progression for those with no improvement. But then, if we decided to combine anyhow, we get, again, a very borderline message. Right? I think that would be clear. So, this is an example of a circumstance in which the investigators would be somewhat torn about how to report if this were thought to be the definitive analysis. So if we made the right call with regarding to collapsing, we get a modest indication of a relationship between improvement and chemotherapy, right? Yeah. Very borderline though, right? Okay. Oh, let's review this a little bit. The outcome actually has 4 levels. That's what we began with. We were considering an assessment based on the 2 4x2 tables. Okay, we looked at that. Then we tried 3 different assessments with 2x2 tables, each with 2 2x2 tables. And we got a different set of things that appear to be interesting. Again, keep in mind, this is just an illustration here, folks. I'm trying to give you a sense of the processes involved here and how one might attempt to interpret. Okay. Because now what we'd like to do is view the ordinal nature of the outcome as important in this assessment. In other words, really what you could make is the case for the 3 comparisons that are different from the ones we argued for initially. Okay. In fact, one approach that is, as we're going to see as we move forward here, that has gained quite a bit of attention and quite a bit of and justifiably so, the analysis of an ordinal outcome based on the notion of a cut. In other words, we'll establish the splitting of this outcome based on the separation between 1 and the other 3, 1 and 2 and 3 and 4, which we've seen before, and 1, 2, and 3 with 4. In other words, the cuts determine the analyses that we would like to consider. So in each instance, we could then argue that we wish to discuss the odds of the outcome being greater than the cut. And in fact, we see that in each case there, those odds are placing the good group as being the better that we'd like to see. In other words, considering the outcome or the consideration of the odds the outcome is greater than the cut is saying the odds of a positive thing in each case. On the other hand, if we spin it the other way and ask for an analysis of the odds that the outcome is less than the cut, then you can see that in each case, then we are spinning it as the odds of the negative in each case. Just to give you that directly here, if we were looked at this particular consideration, that is, say, null hypothesis number 1, we're saying let's compare progression with the other 3, that is, no progression. And if we spin it as the odds of progression, we can see that that is the negative, right? That is essentially the risk group. And that would be the case if we were to use less than, and if you wanted to spin it in terms of the positive, then it would be the greater than. Okay. Maybe I'm going on too long with this. Sorry about that. Okay. We see that in each case we have, if we do decide to use greater than, then we are getting, for example, the odds of any outcome except progression. And then in the second case, it's the odds of improvement. And in the third case, it's the odds of complete remission. So all those 3 are the odds of doing better. Yes. Doing better is sometimes the language that you will see in the use of models and methods that we're going to be coming to for this assessment. But again, as we will see with regard to our assessment using odds, that it doesn't matter whether we spin it in terms of the odds of doing better or the odds of doing worse. Okay, that's though not as obvious as you might think. Okay, so we then have the 3 cut analyses. Okay, we've got the stratified analysis using cut 1. You'll recall this is now the odds, in this case, of doing worse, right? This is the odds. Yes, correction. I'm spinning this in terms of the odds, the odds of doing better, right? Yes. So this is the odds of any, right? This is the odds of anything but progression for those receiving alternating relative to the odds of anything but progression for those receiving sequential. And this is consistent with what we've seen before. Now we're getting odds ratio estimates that are less than 1 because the numerator is alternating and the denominator is sequential. And this is repeated with each cut. Okay. What do we get? In the case of the first cut, we get no evidence of modification by gender, but we get some indication of a relationship between the odds of being anything but progression depending on the form of therapy. And this is consistent with what we saw before. And I'll remind you that if we had written this in terms of the odds of doing worse, the analyses would be the same. All we would be getting is estimates of odds ratios that are then the reciprocals. And you could make the case here that the odds of doing worse might have been the way to spin this. But again, I'm presenting you with the 2 scenarios. We can have the odds of doing better, in which case we see that it is alternating that appears to be inferior. If we were to look at the reciprocals, we would get the same message. And that, as it turns out, is quite specific here to the use of the odds ratio. Nevertheless, and what do we get? We get indication of a relationship that's pretty strong in the first cut, somewhat weaker with the second, and then not at all with the third. Okay. That's, again, 3 analyses, right? 3 analyses that appear to be giving us somewhat conflicting information, but we'll be coming back to this. All right. On the other hand, one could say, and many investigators would say, if we're going to do an ordinal analysis, then these 3 essentially 2-by-2 tables, or these 3 stratified analyses, might be judged to be definitive, and that we interpret our results that we get from these 3 sets of 2-by-2 tables. All right. So those 3 stratified analyses, each with 2-by-2 tables, can be duplicated using logistic regression. The difference here now is that there's 3 logistic regressions. And just for interest here, I'll just show you a portion of this. So we set up the codings as in the usual way, the variables, and then the analyses. And we can then explore, for example, whether or not gender modifies with regard to the odds of anything but regression. Okay, this is cut 1, where I'm then separating the odds of anything but regression. All right, and we could do that with each of the cuts and get I'm showing you the start to each of these analyses. Now, the thing that we have here now is that, well, we have 3 different models we might want to assess with regard to cut 1, and 3 different models with which we might want to assess with regards to cuts 2 and 3. So we've got a fair number of models being assessed here. But on the other hand, this would be the model-based equivalent to the 3 different stratified analyses we might consider. The 3 different sets of 2-by-2 tables, and we have then the corresponding logistic regression version of each of those. And I've shown you the start to this. Now we're coming to what you might want to recognize as, okay, a way of presenting things that at least appears to get around the challenges of having 3 separate analyses based on 3 different cuts. Okay, and we now come to the much newer method in the health care literature, and that is the use of something called a proportional odds model. So it has a somewhat technical looking presentation here, but it's not so bad. Now we're going to have, and we'll spin this description in terms of the probability or the odds of being above each of the cuts. So we'll suppose we have an outcome in which we have, in our illustration, we had 3 cuts. There were 4 levels, and so there were 3 cuts. Okay? And now it is conventional to use the Greek letter kappa here that we will see in a minute corresponds to the cut issue. The Greek letter kappa, the Latin equivalent being the letter C for cut, as we'll see in a minute. Now notice there's a couple of things here. We've got now the log of the odds of being above the jth cut, and we have one set of regression coefficients now that does not involve the cut, and then these coefficients associated with the cuts. Uh-huh. This is something new for us. We can see that each assessment has a possibly different intercept, but the rest is the same for each assessment, okay? For each of the cuts. And the term proportional here, I'll briefly point out to you here, it comes from the fact that if we compare any two log odds here, or the corresponding odds, we see they are proportional. So there's a little bit of lingo here. Okay, we can see that if in fact we are prepared to use this model, then we are making an assumption of proportionality with regard to the odds. And the constant of proportionality in the literature is this exponent of the difference between the kappas. One other point that's worth noting here is because of the additivity here. Now, this part of the model does not necessarily involve additivity, but the comparison between these explanatory variables and the cut coefficients are additive in form. Now, that means that we can see that the regression coefficients for the explanatory variables are the same for each cut. In other words, those characteristics are assumed common to the cuts using our language that we've seen before. And we can see then that that is the key assumption that is maybe a little more approachable than the proportionality of the odds, but rather the fact that the regression coefficients are assumed common to the cuts, and symmetrically here, the cuts are assumed common to the regression coefficients. What are the implications? Well, if we go back to the models we had initially, these three, right, cut-specific regression analyses, right? These were the ones we did. One for the first cut, second cut, and third cut, with potentially different regression coefficients, right? We see that if we look at the difference between any two analyses, so for example, the first cut compared with the second, we see that the difference in the log odds involves the explanatory variables. So this difference between the logarithms is not proportional. Okay? So if we were to take the exponent of this side and this side, we would see that ratio of the two odds is not constant. It's not. There is no constant of proportionality here, but in fact involves the regression coefficients and the explanatory variables. So I hope you can now see that if we are proposing to use the proportional odds model, that if we're going to be judicious here, if we're going to be careful, we ought to assess the assumption of proportional odds. It turns out there are a number of ways to do this. However, perhaps the most widely received and the most widely considered is a test that was established and developed by Professor Roland Brandt, who is a Canadian. Now, it turns out that some time ago, there were methods established for performing this particular test of significance for the proportional odds assumption. And they became add-ons that you could add to your stata in your ADO files. Okay, so you can then add this particular set of ADOs and do's to in your ADO directory, and and then use them for constructing the appropriate tests. And this is available not just in Stata, but I mean such tests of significance are available in R and in other software. Okay. Let's proceed now with an illustration of the use of this proportional odds model and the assessment of that. Okay, we can see then that the model will give us the cut-specific log odds in terms of, going back to our chemotherapy progression of disease illustration, we might then wish to begin with whether or not gender modifies using this assessment. Okay? And it turns out that we're going to get a set of fitted values from such an analysis, and the Greek unknown regression coefficients replaced with their Latin equivalents, and that's pretty standard here. So we'll use B's for the betas and C's for the kappas. All right. Now let's take a look at this, the results. The command that we would use in Stata is called ologit, and O here for ordinal. And now we specify our outcome, which is coded in those 4 levels, 1, 2, 3, and 4. Then we've got the indicator for gender, where we've got this is coded for the females coded 1, the males coded 0, the chemotherapy variable 1 for alternating, and 0 for sequential, and then the product of G with T here, of gender with chemotherapy. Okay. And what we get then is estimates of the 3, if you might like, the usual regression coefficients. Okay. And then the new thing here is the cuts. Now, what I didn't mention earlier was that it is convention in some literature and with some software to use negative signs here. Okay? We're not going to speak to that or whether or not that's a good idea or not, but that's the convention, and that's the one that's used by Stata here. Okay? So what do we get? We get estimates of the 3 betas, and we get estimates of the 3 kappas. Okay, let's take a moment and see if we can't interpret these results. Okay. Each of these estimates for GT, chemotherapy, and gender are estimates that are adjusted for the cuts, because the model was assumed common for the cuts, right? Similarly, these cut coefficients that are presented here are assumed common to gender and chemotherapy. Okay? Now you can see that the Stata then gives us a test of significance for whether or not gender modifies, okay, with the assumption of proportional odds, or, if I may, that this coefficient is assumed common to those cuts. And what do we get? We get no evidence that gender modifies in this instance. So another way to keep in mind here is that what we've done is presented an analysis of gender and chemotherapy with adjustment for cuts. Okay? And further, the interpretation of these coefficients could be done. And you may wish to find some time to write down what exactly is it that each of these coefficients means. Okay? Similarly here. The word assume common or adjustment is important here. So let's just take a minute. For example, the cuts are included in this model without a constant term. Oh yeah, I didn't mention that. There's no constant term here. And this brings up the issue of identifiability, which we saw earlier. We can't have a constant term in addition to the cut terms. That would essentially give us the problems we saw like in the previous session. Now, we can consider, for example, the log odds of being above the cut minus the log odds of being above cut 1. Sorry, the log odds of being above cut 1 minus the log of the odds of being above cut 2. And it turns out that this difference between those two cuts is the same for the males and the females, and it's the same for each of the therapies. In other words, those differences, again, are assumed common. The differences between cut 2 and cut 1, and the differences between, say, cut 3 and cut 1, and the difference between cut 3 and cut 2, those differences are the same for the men and the women, and for the two chemotherapies, right? And that means that we would then could interpret the difference between C2 and C1 as being adjusted for gender and chemotherapy. I think that in a way, a lot of this is the same as what we've seen before, but this is a different world now. We are now discussing an outcome with, in this case, 4 levels, and the cuts then themselves have interpretation, as do the regression coefficients. And in the proportional odds model, both the set of regression coefficients need to be viewed as assumed common to the cuts, and similarly, the cut coefficients need to be viewed as assumed common to the explanatory variables, here gender and chemotherapy. Okay. So the so-called usual coefficients, if I may, or the regression coefficients and their estimates are available to us. So, for example, from that analysis that we just did, if we go back and look at the number minus 0.488, it's saying that for the males, this is an estimate of log odds of doing better with alternating therapy minus the log of odds of doing better with sequential therapy. And we can see that it's negative. Right? We've noted this before. That is, that alternating therapy is doing worse than sequential. Okay? Here we're using the phrase doing better to capture what we meant by being above the cut. And we've adjusted for the cuts. Okay? So the model's regression coefficients, again, to repeat, are assumed common to the cuts here. Okay. Further, we have the ability to test whether or not we should be making this proportional odds assumption. And in fact, the methodology established by Professor Brandt gives us a series of wall statistics and also gives us chi-squared statistics. We have an omnibus test that involves all 6 degrees of freedom, and that is a comparison of all 6 differences, or we can do so for comparison specific to the product of gender and therapy or the 2 individual pieces here, looking for indications of evidence against the assumption of proportional odds. And in this analysis, we see none. Okay? Now, you might argue here that if this were the plan of attack from the beginning, that we were going to use a proportional odds model, we were going to build a series of models and assess the proportional odds assumption. Notice that this assessment of proportional odds we could say, all right, we've done so for this model we began with, which was designed to address whether gender modified, but we could then proceed with an analysis of these of this model without the GT term, or without beta 3 in this instance, and then we would need to repeat the assessments, whether or not we've got evidence of a difference between the chemotherapies adjusted for gender, and whether or not that adjustment for cuts is also credible. So in other words, we would need the models constructed without the GT variable, without beta 3, and then we would need to assess the proportional odds assumption again. Okay, if you're going to be really, you're going to do it, you got to do it. So here is then the details, a little bit about that, which I've already spoken to, right? We've got the 6 degree of freedom test, which can be split into 3 2 degree of freedom tests, giving us some indication of what's happening with regard to all of those regression coefficients that could possibly be assumed common, but maybe not. Okay? And we would see then that we need to proceed. So we see that if we did so, we would have a collection of models that are assessed with regard to the interpretation of the regression coefficients, and also a determination of whether or not there's evidence against the assumption of proportional odds. All of this in play now. So here, for example, is the remainder of this analysis. Here we're using where we've dropped beta 3 equal, we've assuming beta 3 is 0. And what do we get? Well, maybe the big prize here is that we get an indication of a difference between the two chemotherapies. In other words, that alternating therapy is inferior with regard to the odds of doing better than the sequential form of chemotherapy. And we get a low p-value. Okay? Again, you could spend some time interpreting this coefficient. Again, it is now assumed common to gender, but also assumed common to the cuts. Okay? And then we could have what we might view as a crude analysis here, where we don't adjust for gender, wondering whether or not there's any indication here that the gender confounds, all right? Assuming that, again, that there is no evidence against the proportional odds assumption with these two models, if we're prepared to assume that. And what do we get? Well, in this case, the regression coefficient for therapy here, this is the crude, and the adjusted are not materially different. So what we might get here is an indication that gender neither modifies or confounds. Okay? Well, just as we did for logistic regression, we can compute fitted values. Well, in this instance, what is the default is to construct the fitted values using the assumption that the cut coefficients are 0 here, and then get the values, and then we can discuss what those fitted values on the log odds scale are like. And there's merits to the discussion of the interpretation of these coefficients again. The point being here is these are fitted values where we're essentially ignoring the cuts, right? We are setting the cut coefficients to 0. You could say, wait a minute, there's all those sets as well. So here, in a way, what we're saying is these are the estimates that we would have if we were to ignore the cuts, but we have adjusted for the cuts, right? So keep that in mind. All right. The cut-specific fitted values, the comparisons are going to be the same. And I'm going to leave some of these more technical matters for your consideration. The point being is that if I were to inject the cut coefficients into this analysis and then look at differences, we would see that we get exactly the same coefficients as before. Okay. Further, it's a little bit more technical here, but we can construct the fitted values on the probability scale here. It's getting perhaps a little bit technical here, but the display of these fitted values turns out to be very informative, and in fact, the actual display of these fitted values can be very helpful in interpreting these models. So it's a little bit on the technical side, perhaps, but there they are. And in fact, all of that hard work that appears to be the case when one is looking at those formulas on the previous slide, in fact, Stata and or any software we like will, in fact, do the determination of these probability estimates that come from the fitted values very effortlessly. And as I said, we can discuss them and interpret what these values are, and then we can proceed with some displays. Here we have a model that has only chemotherapy, and gender, so there's no graphs per se here, but we could have a measured explanatory variable here, in which case the visuals of these fitted values can be very helpful. Okay. What I have not talked about so far is what do we do if, say, we have an indication either qualitatively in our interpretation of the cut-specific models or in the use of a test of significance for proportional odds. What do we do if we have evidence against proportional odds? Well, if in fact the primary analysis was to assume proportional odds, but then, well, that assumption is discredited, then one could argue for the cut-specific models that we've seen earlier in this session. There are a number of other models that are available, though, and I'm just going to list them here. There is the so-called generalized proportional odds model. In other words, we could attempt an analysis of a model-based approach that does not assume proportional odds. That's available. And then there's an intermediate here that's available to the investigator, and that is if, say, the proportional odds assumption appears to be fine for certain explanatory variables, but not all, we can use something called a partial proportional odds model. And that is also available. So, for example, if we were to look at the Brandt test that is displayed and see evidence of a lack of proportional odds with one or more of the explanatory variables, well, then we can carry out that fit. And again, that's available as a download with Stata. And the so-called generalized ordinal logistic regression is available. Fairly new, and still some literature there on the merits and demerits of these types of models. But what I wanted to do is get to, arguably a little bit briefly here, but a rather completely different approach, which is available to the analyst if, in fact, one is not prepared to assume proportional odds. And that takes us into the whole area of so-called multinomial models. It is quite likely that some of you who are spending time with these sessions are familiar with the multinomial model. And it goes by a number of different names. You will also see it referred to as a multinomial logit. You will also see it referred to as a polytomous logistic regression. And it turns out that this particular type of model is available in Stata using mlogit, and again, it's available with all the other software systems too. Okay, now the point here now is that if in fact we are considering the multinomial situation here, we are at least provisionally abandoning the idea that our outcome is ordinal and assuming the levels to be merely nominal. Now, that doesn't necessarily mean we're completely abandoning the ordinal nature, but as we will see, the interpretation of the use of this multinomial type model is not directly using anything that is of an ordinal type. Now what one is doing is establishing a baseline level for the outcome and considering comparisons with the others. So you're comparing, say, level 2 with level 1, or level 3 with level 1, and so on. Now, in other words, we're not per se using the ordinal nature here. Okay? And what does this look like in this instance? Well, now we're going to have the log of a ratio of probabilities. Where we decide on a baseline group and place that group in the denominator of this ratio. Now, it might then be noting then we're taking the logarithm of a ratio of probabilities now. Okay. Now, this is not directly now interpretable as a log odds, right? This is the log of a ratio of probabilities. It's not the log of pj divided by 1 minus pj, but in fact is the log of the probability in the jth level divided by the probability in that baseline level. Okay. So what we get is logarithms of ratios, and now they are actually rate ratios, or possibly risk ratios if in fact the probabilities are in terms of something negative. Okay, so now we have that the regression coefficients will be available to us as usual, except that now we will have phrases like the difference between the log rate ratio with exposure minus the log rate ratio without exposure. Okay? Or perhaps an explanatory variable is measured, and we'll have the rate of change of the log of the rate ratio per year of age. Okay? So now, even though this model is sometimes called a multinomial logit, we don't directly have a logit link here. Now, there are ways of describing this in terms of logits, but it's rather convoluted, frankly. It can be done, just to say that it isn't without merit that you can spin this in terms of log odds. But again, they're somewhat convoluted and somewhat provisional. Probably better not to do that. Most of the time, I would argue for describing the regression coefficients as I've listed in this display here. In other words, not as odds ratios, but rather as rate ratios. Okay? or as risk ratios. Okay. Well, if we do so, we see that the exponents that we get are the so-called relative risk ratios. Yikes. Yeah. They are the ratios of risk ratios. Okay. And we can have ratios of risk ratios too, depending on how elaborate the model is. Yeah. So again, the discussion of interpretation of these multinomial models is in terms of ratios of risk ratios and then more elaborate forms. It's probably the wisest way to proceed here because of the fact that technically these are not odds ratios, okay? They are in fact rate ratios in general and or risk ratios, and specifically when it's spun in terms of the negative outcome. All right? And here one could argue that maybe it makes sense to choose as the baseline group the outcome where there's no change. Maybe because it's the most commonly seen, as is in the case here. Or that comparisons relative to no change makes sense. Okay. And in fact, well, we do this with this particular circumstance. In Stata, the multinomial model gives us, well, you're going to say here, ooh, now I get 3 sets of regression coefficients, right? So this is progression relative to no change. Here's partial remission relative to no change, and here's complete remission relative to no change. Oh, man. So here we see the first challenge with the use of these multinomial type models, and that is that we don't get one set of regression coefficients now, as we did with the proportional odds model. But, I mean, well, we've made a case that the presumption of proportional odds is not available. So with a multinomial type model, we've got lots of things to interpret. Okay, and so as before, we could proceed with this multinomial model, first assessing whether gender modifies. That's the model that I've presented you with here. And then we could consider the model that does not make the assumption, that makes the assumption that gender does not modify. Okay. Then we've got our busy with interpreting again. And then possibly whether or not gender confounds, in which case we would be comparing this multinomial model giving us now the so-called crude regression coefficients here, right? Again, where we're discussing the log of the risk ratio in this case, right? Without adjustment, and in this case with adjustment. So there's a fair bit in play here, a fair bit of study that's needed. The rationale for interpreting, for using the multinomial model here, which is essentially ignoring the ordinal nature of this outcome, but maybe with good reason. Okay. Now, it is worth pointing out that the choice of the baseline category here does not impact on the fitted values here or in the ultimate set of interpretations. Now, the coefficients will depend on the choice of the baseline, but not materially the actual key comparisons that would need to be made. Okay. So we get, with the multinomial model here, we get 3 sets of regression coefficient estimates. And admittedly, we could get then a repeat again of the issue of assessing modification, assessing confounding, and so on. All using now this alternate presentation. Again, the use of this multinomial model is widely seen in the health research literature. There are options for analysis here, and again, we could proceed with detailed interpretations again. And again, there's quite a bit of technical here, but again, what we're getting is slightly different messaging depending on which model we think ought to be used here or what the circumstances for our assessment are. Okay. So, well, the multinomial approach here, if there's any kind of synthesis, is not making that proportional odds assumption. On the other hand, we're back to 3 sets of regression coefficients again. Oh, yeah. Well. And we could, in principle, discuss how to interpret these regression coefficients. Okay? And I, again, will leave this for your study. Just like with the proportional odds model, the multinomial model can be used to construct fitted values again. And again, in the literature, you do see visual displays of these fitted values informing what's really in play here. And it can be very helpful. Now, the snag would be that if we have an explanatory variable that's measured, that we would then have, in this particular case, a number of curves, okay, that we would then have to interpret and study. That's been done so, and comparatively recently, by Alberta Health Services in a project that they considered, in which they use this particular model. And some discussion of that is included in the folder for session 11. But as is the case here, where both gender and chemotherapy are dichotomous, we get a fixed set of fitted values that are available to us in this instance. All right. Further, just like we had before with the proportional odds model, with the multinomial model, we can construct the fitted values on the probability scale, and there's merit to that. Again, for interpretability, sometimes researchers like to display the fitted values on the probability scale because it gives people something a little more they can grapple with than these, if I may, on the logit scale or on the ratio scale, right? Which is what we got before. And again, just to point out here that Stata does the work for us here. Fairly complicated looking expressions, but the determination of these fitted values is quite easy to do. So here we get on the probability scale. Okay. Now, it is worth noting here that we could have reverse coded the outcome. In other words, maybe we wished to present this in terms of the odds of doing better or the probability of doing better rather than the probability of doing worse, as we've seen, in which case we can do that. And with the proportional odds model, just for illustration here, we get identical results, okay, except that now we are by talking about the odds of doing worse, we get a description in terms of the reciprocals here. So that's available to us. The odds of doing worse, then, with the previous, would be the reciprocals here. However, reversing the coding in the multinomial model does doesn't change the results at all. And you can have a look at this. It is directly available. There's essentially no change. Okay.